This is section 5.6, auxiliary figures and uniqueness. Alright, so the first thing we've got here is uniquely determined. So that's when exactly one thing satisfies a given condition. Okay, an example of this would be your address, okay? That uniquely determines the building that you live in, right? It's because there's only one address for the building that you live in. Another example for this would be your social security number. So like if you had social security number here of like 1, 2, 3, 4, 5, 6, 7, 8, 9, that uniquely determines your social security number. So uniquely determines your social security number. Okay, so those are just a couple examples of there's a certain set number or address or something like that that fits with a certain situation, and that's the only possible one of that. There's not, multiple people with this social security number, or there's not multiple buildings with the same address. Otherwise, that would confuse the post office, right? Okay, so next thing we've got here is on our example sheet, example 1. So in the on the Google site, there should be example sheet that looks like this. So we're going to do the first one here. So tell if each thing is uniquely determined, and if not, say why not. And we can do that with a picture if we would like. Okay, so this first one here, basically we've got to figure out if we've got the angle DEF, if there's only one bisector of DEF, or if we could have multiple bisectors of DEF. So if I've got an angle here, so for A, if I've got an angle DEF, to be uniquely determined, there can only be one possible situation. So if I go and make a bisector here, cutting that directly in half, I have to figure out if this is the only possible spot for a bisector, making those, the same size, or if there's multiple situations when this could happen. So bisector is cutting something directly in half, so there's only one possible way to cut an angle directly in half. So this one would be yes, it would be uniquely determined because there's only one way to cut that angle there in half. Okay, next one here. Given a point A on line M and a point X on line M, given distance from A. Okay, so basically what they want to know here is if I've got some line M, so some line here M, and I've got some point X on it, they want to know if there's only one possible position that is a certain A distance away. So A distance away gives me some other point here, we'll just name it A. Okay, is that the only spot that could be A distance away? So maybe A was like 2. So is that the only spot that could be 2 centimeters or whatever away from that X point? Well, no, it's not. I could also go A distance away on the other side, right? And have another point there. So since there's 2 possible spots that are the same distance away on that line from X, this would not be uniquely determined. Okay, so for B it would be no, and your explanation could be a picture like that, or you could say there's 2 points on that line M that are that same distance away, one on each side of that point X there. Either way would be fine. But that one would be no, because you could be the same distance away on either side of that and still be on that line M. Okay, the next one here, given line N and point C on N, the perpendicular to N through C. Okay, so we've got some line, I'll do it over here, we've got some line here N, and some point C that is on that N. They want to know the perpendicular through C to N. So we want to know if that's the only location that that line could be to go through C and be perpendicular to N. So for this one, I would say yes. That's the only possible place that can be both perpendicular to N and also through C. So that one would be yes. Okay, those ones are kind of tricky. Okay, and actually in that set of stuff there's a list of different things that are uniquely determined, so you could look that over as well. It should be kind of right along this stuff. That might help you kind of figuring out if it's yes or no, but this can also kind of get confusing, so look at it if you want to. If not, don't worry about it. Okay, back to our note sheet here. So we just did example 1, so our next thing here, unique circle theorem on page 283. So if you look at that, it says there's exactly one circle, a unique circle, so unique because there's only one of them, through 3 given non-collinear points. So this is actually what we did in the last section where we had those 3 points, kind of like that, and then we made the perpendicular bisectors between some of the points, between 2 sets of those points. Found that middle spot and then made a circle through that went through all those points. That's basically what this theorem is saying. So this theorem actually matches with the activity that we did in the last section. Okay, so if you've got 3 points, there's only one circle that goes through all 3 of those points, and it's a unique circle because there's only one of them. Alright, the next thing here is auxiliary figure. So it's a figure that's added to a given figure or a picture that we already have to aid in completing the proof. So it's basically you've got a picture to start and they want you to take and add more, well you don't have to, but you can add more onto that picture to help you figure out what's going on. So say maybe you had something like, that, and then some line like that, but then you wanted to say something about a line that was parallel there. You could add that extra line in there, and that would kind of be like an auxiliary figure that would help figure out what's going on in the proof. So it's just an extra picture that's added on to your original picture to help you solve. Okay, when an auxiliary figure is not uniquely determined, so when there's not just one situation, there may be more than one. So like a line parallel to this line here, maybe you had another parallel, that one, there could be multiple ones that would fit that situation. There might also be none that fit a situation. You might see that as well, okay? But these aren't terribly important. They'll come up a little bit in this section, but in the big scheme of things, they're not horribly important. Okay, next thing we'll be back on that example sheet. So we'll look at example 2 here. Now I hate this example here because I feel like it makes no sense with this picture, but we'll talk through it because it is part of this lesson. So we've got triangle ABC, and then a student wished to draw an auxiliary line, the perpendicular bisector of this segment AC that passes through the vertex B, and then it says, is this always possible? So what I don't like about this is it asks you that question, but then it gives you this picture that fits exactly that situation. So I feel like it makes it pretty obvious that it's not always possible, right? Because if we're thinking through what they're talking about here, so they started with this triangle and then they added this auxiliary line, just kind of an extra line through there. So what they wanted is they wanted this to be a perpendicular bisector of this segment. So basically, it's at 90 degrees and it's splitting that bottom segment into 2 equal parts. But they also wanted it to go through that point B there. Well, you can see here when you make that perpendicular bisector and shoot that line up, it's not always going to go through B, right? Now it could possibly go through B if this was a isosceles triangle here. If that was, your middle point there, you got A, C, and B. If that's directly in the middle, then it would be a perpendicular bisector between those. So if this is isosceles where those two are the same, then it would work, but it's not always going to work, and it's based on this situation here. So like I said, I don't love this one because they already start with the picture, but for the purpose of what we're doing, we should talk about it. So this would be no, it's not going to always be possible. So no, and then you could say, like in this picture here, doesn't have to go through, so it doesn't have to go through point B. Now it could go through point B, like I said, if it was an isosceles triangle there, but there could be situations where it doesn't necessarily go through there, okay? So just kind of be careful on ones like that, but that's kind of a weird question. I wouldn't ask something weird like that on the test. Okay, what do we got next here? Activity. Okay, so on page 283, we'll look at that activity. So it says we are supposed to draw a quadrilateral, ABCD, in which the diagonal, the segment between A and C, does not lie on the bisector of angle A. Okay, so see if you can come up with a picture that would have four sides, because that would be quadrilateral, and then when you connect between your A and your C, you don't want that to bisect angle A. Okay, so see what you can come up with, and then I'll draw some examples in here. Okay, so for some examples, you could make something that kind of looks like a kite. So maybe something kind of like that, where this is our A, our B, our C, and our D, because then now when we go and we connect between our A and our C, you can see there that that's not going to be a bisector of angle A, because that angle there is going to be smaller than that angle there. So that would be an example where it's not going to be a bisector. You could also do maybe something like, kind of like a little trapezoid deal, or maybe you had something like that. You go A, B, C, D, and then when we connect between our C and our A, you can see that this angle is quite a bit smaller than that angle there, so that would be something. You could also do, these are called darts, which we'll talk about in some chapters down the road. Something like that. Not a great picture there, but you could go A, B, C, and D. So when you connect and make a diagonal between the A and the C, this one's actually going to go outside the shape, but that's not going to bisect that angle A, because A would be inside of here, and it's not even going to cut through that. It's going outside of the shape. So any of those would work for not making it a bisector. Now for this next one, they want it to be a bisector. Okay, so they want you to draw a quadrilateral again, and they want the diagonal between the F and the H to appear, so you don't have to measure it or anything, but to be a bisector or splitting angle F in half. Okay, so see if you can come up with some pictures there, and then I'll draw some in. So one of them you could do would be like a square. So if you did a square, and we'll just throw some letters on here. If you go from F to H, it would split both of those into 45-degree angles. Okay, so 90 split directly down the middle there. That would give you 45s. You could take like our kite and our dart examples that we had before. So with the kite, if I can get this good enough here. If we go, so change kind of the way our letters are here. If we go and we go from F to H in this situation, cutting straight down like that, those two would be the same. Okay, so that would work. We could also use the dart example. So hopefully I can draw this good here. Not great, but it'll work. Okay, so imagine that's a little bit better there. But if we label this one as F, E, H, G, when we split here from F to H, those would come out to be the same. Okay, so those are just some different examples of ones that would work. So basically each side has to be a reflection of itself to be able to split there. So you want, like, you know, your F to H to be like a reflection line between like the G and the E, and then, you know, kind of the same, or not G and E, yeah, G and E. Same thing here and same thing here. Okay, so it kind of shows as a reflection line. Okay, what's next here? Uniqueness of parallels theorem. So that is on page 284. So through a point not on a line, there's exactly one line parallel to the given line. Okay, so let's kind of sketch this out here. So what that means, and we're going to draw some auxiliary lines in here, is we've got a line L, and or you could call it RQ, either way. So we got that line there, and then we've got some point P that is not on that line, and what they're saying is there's one line that runs parallel to this line here and through that point. Okay, so let's kind of draw this out here. So what we want to do to start is we want to take and we want to draw in the line from P to Q. So I'm just going to take a straight edge, and I'm going to shoot from P to Q like that. Probably didn't need to be that long, but you get something like that. Now what they want us to do is to label this angle here, PQR, as angle 1. And then they want us to use alternate interior angles, which we talked about before in this chapter, to make an angle basically here that's the same as that angle 1. So if we make, so basically we want to come up with like a parallel line shooting across like this somewhere, where this angle here and this angle here are exactly the same. So what we can do here is just figure out how big that angle actually is, and everyone's will be slightly different because everyone drew their own. So you just put your center of your protractor on that point Q, measure out there. Mine looks like it's about maybe like 37-ish, and then you do that same 37-degree amount, or whatever you get, coming off of your P. So I'm going to go out here to 37-ish, put a little mark, and then I'm going to shoot a line from my mark to that P point. It's kind of like that, and that should, if you did it well, it should look like it's parallel to that one there. And then that angle right there, and that angle right there, and then they wanted us to throw an A on this. Those two angles would be equal to each other, and that's the only possible line that can be parallel to this line here through that point P. So that's why it would be uniqueness, because it's the only possible situation that can be parallel and through that point. Now if we just wanted parallel, like say this was our original line and they just said parallel, well you could have there, 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 there. With parallel you have a whole bunch, an infinite amount, but if they're specifically saying through a point, that's when it becomes unique. Okay. Alright, next thing here, non-Euclidean geometries. So there are geometries that we've talked about before that are non-Euclidean. So it's basically you have to use different postulates and theorems in those. So at the beginning of the year we talked about graph theory and discrete geometry. Those would be examples of non-Euclidean. Another one that sometimes people study is hyperbolic geometry, which is basically like spherical geometry. So if you think about the lines on like a globe, so like the lines of longitude and latitude, those meet like at the North and the South Pole, where they look like they're kind of parallel as they're going, but then eventually, because they're going up on a circle, they end up meeting each other. So that's going to have different rules for things like this with uniqueness than when we're talking about our Euclidean geometries, which are on like a flat surface or could be graphed. Okay, so you just have to kind of be careful. If you do end up doing different geometries, not all of these same things will apply to this. But we only focus on Euclidean geometry, so you don't have to worry too much about that other stuff. Okay, we got one more theorem here. So triangle sum theorem on page 285. So that says the sum of the measures of the angles of a triangle are 180 degrees. So basically what they're saying here is this angle, and this angle are all going to add up to be 180, which is probably something that you've known about for a long time, probably when you first started learning about angle measures and shapes. So you probably knew that the corners of a triangle add to 180. You might not know why it does, so I'll kind of show you here. Let me get a different marker. So the reason that it does add to 180 is dealing with kind of parallels like we were talking about. So I'm not actually going to draw a parallel in where I measure it. I'm just going to kind of guess. So what I'm going to do here is I'm going to draw a line, and I'm just going to guess, like I said, that's parallel to AC through this B here. So I'm just going to kind of line up like that, shoot a line like that. Imagine that that top line and that line there are parallel to each other, and then I'm just going to throw some points E and D on this just for the purpose of talking about it. So how this works here and why this adds to 180 is dealing with our alternate interior angles. So if you think about this here, basically we know this one, and this one add up to be 180. Well, dealing with alternate interior angles, I know this angle A here would be alternate interiors with EBA right there. And then I also know that this angle C right there, getting my marker all messed up, is an alternate interior following the zigzag here with DBC, that one there. So whatever those two are added together, plus this one here that is in between those, so that angle B that's being shared, you know, both on this straight line here and then also with that triangle, if I take this one, and this one and add those together, that's basically like a, it's not really a linear pair because there's 3 of them, but they're going to add to 180, right? So if I take this one, and this one, since it's all on a straight line, those all add up to 180 degrees. So since this one and this one are the same, and this one are the same, and I'm sharing that same B with both of those, that's why the triangle also adds to 180. Okay? Probably more than you wanted to know, but that is why it works. But the important thing there is all the angles of a triangle add up to 180 degrees. Okay, so this is your book page that goes with the assignment. So page 200, and it's not the 284, it's 286 is the actual page. And then you're going to do 1 through 5, 10 to 12, and then 14 to 20 even.